The topic for this part of video lecture is circular motion in horizontal plane. And what you see on the screen is a common sight, and hope all of you must have experienced this kind of merry-go-round. So here, if you carefully observe in a steady state all the people who are there in the merry-go-round, what kind of motion they are experiencing, all of them are undergoing circular motion in a horizontal plane. A similar kind of setup is also possible by using a string and a small particle called bob attached to it. So if you hold the string at a particular angle theta from the vertical, and for a right speed given tangential to right speed in tangential direction, this bob also can be made to go in a circular motion in horizontal plane. Other examples are, if you take a kind of cone or a funnel, a smooth cone, again here also with proper setting, with proper speed being given to this object here, it can be made to undergo circular motion in a horizontal plane. Similar arrangement is possible inside a hemispherical bowl also. Again, all cases speed has to be appropriate. That's what we are going to study in this part of video lecture. So what are the key points? What are the key things we need to keep in mind for particle undergoing circular motion in horizontal plane? Let's look at a particle which is having this kind of motion, and this is the top view. We are looking from the top, this trajectory of the particle here. Speed is v. First thing, summation of forces in vertical direction has to be equal to 0, or vertical component has to be equal to 0. The reason is quite simple. As the definition goes, the particle always remains in same horizontal plane. It means its y coordinate or vertical coordinate is not changing, so there is no displacement, no velocity, hence no acceleration in the vertical direction. Summation of force in y direction has to be 0. Second important thing is, what is the coordinate system we should choose to analyze circular motion in horizontal plane, because choice of proper coordinate axis makes the analysis simpler. As in case of all circular motion, choice of coordinate system should be towards radial direction and tangential direction. So we should always choose a coordinate system. So we should choose an axis in the direction in which the acceleration is known. Here, in case of circular motion, we know the acceleration in the radial direction. Hence, one direction must be radial, other is tangential. What is the third possible direction here? Vertical. Vertical direction in this particular case will appear like a dot, because that would be perpendicular to the plane of motion. So typically all three coordinate system might be involved in case of circular motion in horizontal plane. So coordinate system, that's our coordinate system, not typical x and y coordinate. So when we draw the free body diagram also, we'll resolve the forces along tangential, radial and vertical direction, not xy coordinate. So once we draw the free body diagram, what would be our equations of motion? One in the radial direction. Sometimes we also use a name centripetal or normal. All three have the same meaning. So we'll use the term radial. So summation of radial component of forces will be equal to mass into radial acceleration. What is radial acceleration? Either it can be expressed in terms of angular velocity, which is equal to r omega square. Hence, sigma fr will be equal to mr omega square, or it can be expressed in terms of linear velocity, mv square by radius of circular motion. So depending on what information is given in the question. And this force is called centripetal force. The reason is quite obvious, that this is a force which is directed towards the center. And this is the force which is responsible for making the particle move in a circular path. And what is the other component? Summation of tangential component of forces has to be equal to mass into at. At is my tangential acceleration, which is also equal to dv by dt. So this, for circular motion, radial acceleration is always present. Without radial acceleration, circular motion is not possible. Whereas tangential acceleration may or may not be there. It could be positive, it could be negative, or it could be zero. It will be zero in case of uniform circular motion. If it is positive, the speed will keep on increasing. So we'll start with a simple example of circular motion horizontal plane. Consider a turntable rotating at uniform angular velocity omega about a vertical axis. What is turntable? Is similar to a gramophone record, the old gramophone record, a black color. So when you set it up, when you put it on, it will undergo circular motion about a vertical axis, and in a steady state the angular velocity will be constant. So different kind of gramophone record will have different RPM, so standard RPM, so that can be converted into angular velocity. So this is a turntable rotating at uniform angular velocity omega about vertical axis. Now if we place a small block of mass m at distance r from the center, what is the motion of the block if the disk is smooth? So disk is rotating, we place a block m at a distance r from the center. What kind of motion this block will have if the disk is perfectly smooth? Think for a second what your answer would be. Actually, this block will stay at rest. If you think it will undergo circular motion, it will not. The reason is pretty simple. Only forces which will be acting on this block would be in vertical direction. mg vertically downwards and normal reaction vertically upwards. Since the disk is smooth, there is no frictional force. So there is no horizontal component, hence there is no centripetal force. It cannot undergo circular motion. What will happen if the surface is adequately rough? So we have a turntable, surface is rough, we place a mass here and we set this in motion. Gradually increase the angular velocity till it comes to steady angular velocity. So if the surface is adequately rough and it in steady state, it is rotating with angular velocity omega. In that case, what does adequately rough mean? The word adequately rough means friction is large enough to prevent any slipping. So moment this word is there, it means no slipping will take place when the disk is undergoing rotation with angular velocity omega. Hence this mass also will undergo circular motion with angular velocity omega, and this would be its path. Now what would be free body diagram of this block at the instance shown? The direction of forces may keep on changing at different times. At this instance, what will be the free body diagram and what will be the direction of net acceleration? Or you can think in terms of what will be the direction of net force. This should be simple enough to answer. Since it is undergoing uniform circular motion, there is no tangential acceleration, there is no vertical acceleration, only acceleration is towards the center, radial acceleration. That would be the direction of net acceleration. Hence, that would be the direction of net force as well. Vertical force is 0, tangential 0, only in the radial direction. And this would be the free body diagram. Three forces acting. One force is weight, mg. Normal reaction equal to mg because there is no net force acting in the vertical direction. So these two forces equal and opposite. And third force is friction force. Initially, even if we do not know what the direction of friction force will be, from the nature of circular motion, we know the net force must be in the horizontal plane directed towards center. And since only force which is acting in the horizontal plane is frictional force, the direction of the friction force must be always toward the center. So if this block, the direction of friction force will keep on changing, and such that the frictional force is always directed towards center. And what would be the magnitude of friction force? That also can be found out using equation of circular motion. Summation of radial component of forces will be equal to mass into radial acceleration. So we substitute these forces here, force only one force m, mass into radial acceleration, which is mr omega square. So this, from this equation we find the friction force which must act on this particle if it is undergoing circular motion is mr omega square. Another way of saying is friction force is the centripetal force here. Another similar example, A mass m is tied to string and it is having uniform circular motion of radius r on a smooth surface, a smooth horizontal surface. So this is a smooth table. Something similar to smooth means something similar to the table what you see in case of air hockey, and this is the puck what you see in case of air hockey, attached to a string. The string is through hole connected to another mass m2, and for an appropriate combination of velocity and radius and of course m2, it can be made to move in a circle of constant radius, constant speed. What is that combination? Let's see. First thing, what is the direction of resultant force and acceleration? So think for a second, what is the direction of resultant force or acceleration? Towards center. Because again, basic property of uniform circular motion, resultant force and acceleration is only towards center. Other components are zero. So this would be the direction of resultant acceleration as well as force. So both have to be in the same direction. So which force acts as centripetal force? In previous case we have seen the centripetal force was due to friction. What is the centripetal? Here there is no friction. So which force will provide centripetal force? Tension force applied by the string will provide the centripetal force. The moment you cut the string, it cannot have circular motion. It will take a tangential path. It will have a straight line motion, rectilinear motion. So what is the free body diagram at the instance shown, and what is the net acceleration? If you draw the free body diagram, again similar to previous one, three forces, but in place of friction force, there is a tension applied by the string. So if we write the equation of motion, the summation of radial component, only one force T has to be equal to m into AR, and radial acceleration is v square by r. Since here velocity is given or speed is given, we will substitute v here. So this will be T will be equal to m1 v square by r, and since the radius is constant here, this mass m2 which is hanging underneath the table also will have zero acceleration. Hence tension has to be also equal to m2 into g. That's the equation of motion in case of the object which is having this kind of motion. Now if we compare this example with the previous one on the turntable, rough turntable, what are similarity and differences? Both cases we notice the free body diagram is very similar. These two forces are identical. In previous case, since it was a rough surface, there was a friction force. There is no friction here. So here the centripetal force is provided by tension force. And other difference what we notice, previous case both object and surface were in motion. Here object is in motion, surface is at rest. So both cases circular motion are possible. Let's move to another example. Consider a car, mass is m, it is moving in horizontal ground in a circular path at constant speed v. So this is the top view. So car is moving in horizontal ground in a circular path at constant speed v. So you imagine you are looking from the top from a helicopter. So this is a kind of view you get. So the figure what is drawn is in horizontal plane. What is the direction and magnitude of resultant force? What kind of motion? So if you have to visualize this motion, suppose you are driving a car if you have a big ground, you keep the speed same. You can look at your speedometer. Speedometer is showing the constant speed v. If you turn your steering towards left and you keep the steering turned at constant angle, it will undergo this kind of circular motion. So what will the direction and magnitude of resultant force? Uniform circular motion. Hence net force has to be in the radial direction and has to be equal to mv square by r. This has to be the direction of resultant force equal to, and what are the forces acting on the car and what is the source of centripetal force here? Here again the free body diagram is very similar to the first case on turntable. Only difference was there the turntable also was in motion and the block was in motion. Here car is in motion, surface is not in motion. Still the friction force remains the same. In both cases the object has a tendency to slide outwards. Hence the friction acts in the towards the center. So force acting, so here also the source of centripetal force is friction force, and if we write the equation of motion, summation of radial component is equal to mass into radial acceleration. So F is equal to mv square by r, and friction force must always be less than maximum possible friction force, which is equal to mu mg. So F has to be less than or equal to mu mg. So what will happen if, suppose earlier you were driving at 40 kilometers per hour, you increase the speed to 50 or 60, increase the speed, what would change? These forces won't change, but friction force will change. As the speed becomes higher, the friction force also must increase in magnitude. The friction force also will increase. But if we keep going at higher and higher speed, will the friction also keep increasing forever? No. We know the friction force has a maximum possible value, and maximum possible value is mu times the normal reaction, which will be equal to mu times mg here. So if speed becomes high enough such that the friction force becomes equal to mu mg, that speed is called maximum speed on a rough surface. The equation for maximum speed is mv max squared by r is equal to mu mg. And what will happen if we go speed higher than this? If we try to go higher than this, the vehicle will, if we go higher than this, the car will not be able to follow this circular path. It will try to skid. Skid means it will take a path which will have a radius larger than r. That's called skidding. So any speed higher than the value given by this equation will lead to skidding or motion of a car in a larger radius. What happens when the speed is lower than this equation? If the speed is lower than V max, in that case friction will be within limiting friction, or which so friction force be less than maximum possible friction, which will be static friction. At V max, limiting friction, and higher than V max, kinetic friction, and lead to skidding. Let's come back to what we have seen in the beginning of a video lecture is something like a joyride or merry-go-round. We have taken only one part of merry-go-round, which is a conical pendulum. Let's first understand what is a conical pendulum. You can also take a string, attach a bob or any small particle to the string, hold at certain angle. If you give an appropriate tangential velocity, you can make this bob undergo circular motion in horizontal plane. If you give speed, if it is not appropriate, it will have more complex motion but not the circular motion. So it will have this motion in horizontal plane, circular motion, for a proper combination of theta and v. I am assuming the L is constant here. So this V there has to be proper relationship, then only it will have this kind of motion, and that's what we'll find out, what is the relationship between V and theta. So particle M will move in circular path in horizontal plane for right combination of V and theta. So at this instance, what is direction and magnitude of resultant force? By now should have been easy. It is undergoing circular motion in horizontal plane, hence net force also must lie in the horizontal plane towards the center. This is the direction of resultant force and has to be equal to mv square by r. So what is the free body diagram at this instance? Easy enough to draw. Only two forces acting, gravitational force and tension T applied by the string. The string makes an angle theta from the vertical, hence tension also will make an angle theta from the vertical. So this would be these are the forces acting mg and t. What is the choice of coordinate axis? Of course, one direction. Here, unlike previous cases, this is a side view. This is not a top view. So what are the directions we can view from here? We can view the radial direction, and this direction is vertically upward direction. And in this figure, can we mark a tangential direction? The tangential direction will be perpendicular to the plane of the screen. It will be into the screen. So we can mark tangential direction only in form of a cross mark here. So what is choice of coordinate axis? Of course, in case of circular motion, one axis must always be towards radial direction, and other is, since we know vertical forces must be 0, other is in the vertical direction. Thus the choice of coordinate axis. One radial direction, another in vertically upward direction. Then we resolve the forces. So basically we resolve T, mg is already in the vertical direction. So when we resolve T, this is T cos theta along y direction and T sin theta along radial direction. Now we can form the equation. First equation what we form, summation of y component of forces equal to 0. So which gives you T cos theta is equal to mg, or T is equal to mg by cos theta, which indicates the tension in the string is always greater than mg. So tension in the string will be greater than the weight of the bomb. In other words, vertical component of tension balances the weight of the bomb. How about radial direction? This would be the equation in radial direction. Radial force is T sin theta. T sin theta has to be equal to mass into radial acceleration, which is v square by r. What is r here? R is what? R is the radius of circular motion. This is the circular motion. Where is the center? This is the center. What is the radius? This is the radius. So it is not L. What is this radius? Actually L sin theta is the radius here. So T sin theta is equal to mv square by r. So what we can say here, this is equation. We say horizontal component of T provides centripetal force. The vertical component balances weight, and horizontal component of T provides the centripetal force. How much is the centripetal force? We substitute T as mg by cos theta. So centripetal force here is equal to mg tan theta. This entire Fr is equal to mg tan theta, which is horizontal component of tension. Has to be equal to mv square by r, r being equal to L sin theta. So this equation, we just cancel out and rearrange the terms. V square is equal to rg tan theta, or v is equal to root gr tan theta. That's important relationship you should remember. In case of, so what is theta here? Theta is the angle the string makes, or better way to remember this theta is, this equation is valid when only two forces are acting. One is gravitational force and other force is acting at angle theta from the vertical. So this angle T, what angle the T was acting? At theta from the vertical. If such kind of forces exist, it will give rise to circular motion in horizontal plane, and this would be the relationship. V square is equal to rg tan theta. So what will happen if we increase the speed here? If V becomes higher, the right hand side also has to increase. So theta will increase, and as theta increases, automatically R also will increase, because R is nothing but L sin theta. So as V increases, both R and theta will increase. So if we increase the speed here, then we must also increase theta, then only it will undergo circular motion in horizontal plane. So in case of merry-go-round also, you would have noticed initially when it goes at a lower speed, when it begins its motion, the angle the strings suspend, those ropes make with the vertical are smaller. As it picks up speed, as the speed becomes higher and higher, you will find the angle theta also keep on increasing. That's what this equation indicates. Higher V, higher theta, and this is the equation. Another thing what we notice here, there is no mass term, which basically means in place of mass, if we are replaced with another bob of a different mass, it still gives same velocity at same theta. If mass m is undergoing circular motion, mass m by 2 also will undergo circular motion, mass 2m also will undergo circular motion of the same radius, as long as v and theta are same. It is independent of m. So in case of merry-go-round also, it doesn't matter what the weight of the person is. It could be a small kid of lower mass, it could be a fat old man of much higher mass. Both, when merry-go-round is rotating in a steady state, both will make same angle with the vertical. It is independent of m. Now we come to conical pendulum. This is similar to conical circle. Now we come to time period. So when any circular motion will keep repeating itself, if the full circle is completed and if it is uniform circular motion, the time at which it keeps repeating itself is constant, called time period. Or other way to define the time period is time taken for particle to complete one full circular motion. So we can calculate time using standard definition of speed. What is time? Distance by speed. Why are you using this? Because speed is constant. And what is the distance it travels in one full circular motion? Perimeter. So time period is equal to perimeter by speed. And if we substitute v is equal to root gr tan theta and rearrange the terms, we find t is equal to 2 pi root L cos theta by g. So what will happen as speed increases? If we increase v, what is the effect of v on theta? Theta will increase. As the theta increases, cos theta decreases. At higher speed, time period is lower. At higher speed, it will take less time to complete one full circular motion, which makes sense. So in case of merry-go-round also, when you start your motion, initially speed is lower, theta is smaller, it will take longer time for you to complete one full circular motion. As the speed increases, theta will increase. You will trace out a circle of larger radius, so you will cover more distance in one full circular motion, yet you will take lesser time. So time period, this is the time period in case of conical pendulum. So this what our understanding is, as v is increased, its inclination vertical will increase, and so will be the radius. Now let's take, so all this what we had done, it was based on what kind of forces? These forces acting, mg and tension, vertical component tension being equal to mg. And this was giving rise to uniform circular motion in horizontal plane. So what if we make slight change in the free body diagram without changing the net force? How do you make this change? By what we call the translation. Let's look carefully. So what we do here, the T was acting like this fashion. Now we replace this T with a normal reaction. We have just shifted. If the magnitude of N is same as magnitude of T, is there any change in net force? No. Net force remains the same. If the net force remains the same, then motion also should remain the same. So how to obtain this kind of force arrangement? So tension we can obtain through strain. So if we have a surface at angle theta, we can get this kind of force arrangement. Let's see how do we get this kind of force arrangement. If we have this is a cone, and cone surface makes an angle theta with the horizontal, and axis of the cone is kept vertical. If I place an object here, this object also will experience only two forces, mg and normal reaction acting at angle theta from the vertical. If this angle is theta, N also will make theta from the vertical. So always keep in mind, this formula what we use is for angle theta from the horizontal, not the semi-apex angle. When we talk of semi-apex angle of a cone, this is the semi-apex angle measured from the vertical. But in this formula, we will use angle made by surface of the cone from the horizontal. So in this case, if we keep an object here with appropriate speed given in tangential direction, this can be made to go in a circular motion in horizontal plane. So if N is same, if vertical component of N is equal to mg, so net horizontal force in this case also will be same as before, which was mg tan theta. That would be my centripetal force. So what has the relationship? What speed v it is possible? So again, unless I give a speed v which matches with this relationship, then only it will undergo circular motion in horizontal plane. V is equal to root gr tan theta. What is r here? This r is the radius of the circle. This is r. This is the radius. And this r will depend on h. So r tan theta, h by r is equal to tan theta, or h is equal to r tan theta. So depending on, so what we notice here, v square is equal to gh. It means higher the velocity is, it will undergo circular motion at a higher level, tracing out circle of larger radius. So which makes intuitive sense also. If we keep at a lower level in the cone, I need to give a smaller velocity. If I keep this particle at a higher level, it has to trace out a circle of larger radius, and velocity which need to be given also will be higher. So this is the relationship. Again, it comes from same V is equal to root gr tan theta, as the force arrangements are similar. Another possible arrangement is, let's look at this case. For which part of the cone is exerting this normal reaction on this object? Only the part of the cone which is in contact. Rest of the cone doesn't really matter for this motion. That's what happens in case of highways. So motion of vehicle on a banked road. So this is a side view. We are looking at a road from the side. This is horizontal line, and road surface is not horizontal. The outer surface of the road has been raised. It is making an angle theta with the horizontal. The motion of vehicle on a banked road. What is angle? Angle the road surface makes with the horizontal is called angle of banking. So here, which part of the road vehicle is in contact with? This is the part of the road vehicle is in contact with, and if this is the radius of circle, radius the road surface makes in the horizontal plane. R is the radius of circular motion. So vehicle will move at the same level. Vehicle will undergo circular motion in horizontal plane. So if it is undergoing circular motion in horizontal plane, by now we know the net force acting on the vehicle is equal to mg tan theta. Again, the vertical component of normal reaction will balance the weight, and horizontal component of normal reaction will provide the centripetal force, which will be equal to mg tan theta. Hence, V square is equal to gr tan theta. What does it mean? It means on this, for any particular road we take, the radius the road makes is constant. And once we lay the road at a particular angle theta, theta also is constant. Only thing which can change is vehicles can travel on the road at different speed. That's the variable. So if speed is such that which meets this equation, only one particular speed will meet that equation, equal to root gr tan theta. If the vehicle is traveling at that speed, in that case, no friction force will act. So banked road at a particular speed, which is the most common speed at which vehicles travel. So if we bank the road at that speed, all vehicles which are traveling at that particular speed will not experience any friction. So suppose I have an expressway. I want a majority of the vehicles to travel at a speed of 80 km per hour. In that case, I will design angle theta such that for V is equal to 80 km per hour, this equation balances. So only at a particular speed, no friction will act. But some vehicles may travel faster, some vehicles may travel slower. In that case, what will happen? At higher speed, friction will act downwards. And if the vehicle is traveling lower than the speed given by this relationship, then friction will act in the upward direction. So what does downward direction means? Down the slope, it has to act parallel to the slope. Upward direction is along the slope, up the slope. Another example of normal reaction in mg, normal reaction at angle at theta, is if we take a bowl, a hemispherical bowl, a smooth bowl of radius small r. We have been using capital R for radius of circular motion. Small r is the radius of spherical bowl, hemispherical bowl. So here also, if we place an object here, so which part of the ball is applying force? Only the part of the ball which is in contact. So I am concerned with the slope of which part of the ball? Only the part of the ball which is in contact. What is the slope of the surface which is in contact? If I draw a tangent, the angle made by the tangent with the horizontal is the slope of surface. So if this angle is theta, it is equivalent to, if I replace this ball with the inclined surface at angle theta, like a cone, both will provide same type of force. So this ball also will act similar to a cone of angle theta for this radius. If the radius changes, angle theta also will keep on changing. That's the difference between cone and the spherical ball. In case of cone, everywhere the angle remains same. In case of spherical ball, smaller radius, angle theta is smaller. As r keeps on increasing, the theta also will keep on increasing. So in this particular place, the angle made with the horizontal is theta, Hence, the forces are very similar to previous case. Free body diagram is same. So at what speed I should project this object here so that it undergoes circular motion in horizontal plane? This equation, same equation as before. Root gr tan theta. V square is equal to gr tan theta. So a particular point, if at this point I can calculate what the theta is, what the r is, I substitute the values, calculate v. If I give that velocity in the tangential direction, this particle will undergo circular motion in horizontal plane. What happens if we give higher velocity? Higher velocity then will tend to move up and have a more complex motion. If I give velocity lower than what is calculated by this equation, it will not move horizontally, it will start moving downward spiral. Only at a particular speed satisfied by this equation, it will undergo circular motion. And as you notice, as we r keeps increasing, as suppose if we increase v, then what will happen? If you want to give higher velocity, then radius also has to be higher, and automatically theta also will become higher. So to make it move in a circular path at a higher speed, it will go at a higher level. So height from the bottom will change. So there is a relationship between h and velocity. So in this equation, we can substitute h also. If you have to calculate h, what is h equal to? H is equal to, this is equal to, from here, this height is radius, and from here to here, this angle will be theta. So h will be equal to r into 1 minus cos theta. So we can calculate through substitution, we can calculate the height also of a particular velocity. At what height it will undergo circular motion. Higher the speed, higher is the height. Lastly, let's consider motion of a car mass m moving at a constant speed v on horizontal curved road as shown. What is the view? We are looking from the top. It is moving the constant speed, and this is the path it follows. It passes through point A, B and C. So this part of the curve, radius is R1. This part curve also has some radius. So mark the direction of weight and normal reaction at A. Can you mark the direction, normal reaction and weight at A? Just remember it is top view. So this entire diagram represents horizontal plane and mg and normal reactions are vertical. So we cannot draw these forces as arrow. We have to mark these forces as dot and cross. How about both are perpendicular to plane of motion, hence can be marked only as dot and cross. Can we mark the direction of friction force on the car when it is at A, B and C? So which plane the friction force will act on is undergoing circular motion in horizontal plane. Friction force also will act in the horizontal directions towards the center. Uniform circular motion, hence friction force also will be towards center, providing the centripetal force. Its direction will be towards center. So this would be the direction of friction force at A, and this would be the direction of friction force at C. At B it is moving in a straight track, no friction force will act. So this brings us to the end of circular motion in horizontal plane.